Good afternoon.
Good afternoon, sir.
Okay, is screen visible?
Yes, sir.
Okay, so do you remember what we were discussing last time? Yes, what we discussed. We were talking about continuous function on interval, right? So recall. So what is bounded function? Right? So what is a bounded function? F from A to R is bounded on state A if there exists some number such that absolute value of fx is less equal m for every x in A. Then we discussed boundedness theorem. And what is the statement of boundedness theorem? If I is equal to is a closed and bounded interval, second, f from I to R is continuous, then what is the conclusion? Yes,
F is bounded on I.
right. So f is bounded on interval I. So f is bounded on interval I means what? There exists some constant such that absolute value of fx is less than or equal to m, right? For every x in I. Okay, so statement is clear, right? And we discussed proof of this, and proof is clear. We already discussed this. What is algorithm? What is algorithm to prove this, or what is the proof? What we assume, f is not bounded on I, that we assume. Then what we found, suppose f is not bounded, then there exists a sequence xn in I such that fxn is greater than n, right? Then what? Xn is bounded sequence, so that by Bolzano-Weierstrass there exists a subsequence xn k of xn. There exists a convergent subsequence xn k of xn, right? So limit of xn k is equal to x. Then x is member of I, right? Then f is continuous at x, and therefore f is continuous at x. So limit n tends to infinity f of x and k is f of x. What does it mean? F x and k is bounded sequence, right? Then, but f of x and k is greater than n k is greater than k for all k contradiction. Right, so this was the algorithm of proof. Do you understand? Is it clear?
Yes, sir.
Right, so if you remember this algorithm and how this algorithm works, at each step there is a reason, and then we get a contradiction. So we accept that f is bounded. Fine. So remark. So in boundedness theorem, so what is our boundedness theorem? I am writing it again because we want to interpret in different ways. So what was boundedness theorem? I is equal to AB is a closed interval is bounded. Third condition, f on I to R is continuous, right? And then what is our conclusion? F is bounded. Right, this is our theorem. Okay, let me call this as a statement P. Let me call first as statement P, second as statement Q, third as statement R, and conclusion as S. So what is the boundedness theorem? P and Q and R implies S. Logically, is it correct?
Yes.
Yes. Now, if one of the condition is not satisfied, if one of the conditions 1, 2, 3 fails, then the conclusion of boundedness theorem may not be true, right? So one of the condition fails means what? For example, if I define f of x, function f from 0 to 1 to r. Okay, so if I define function f on 1 to infinity to r, f of x is equal to 1 by x. Okay, now which conditions are satisfied in the boundedness theorem and which conditions are failed? So first, is f continuous? On domain? Yes.
Yes, sir.
Yes, no problem. So function is continuous. Is domain I is equal to 0 to infinity closed? Is it closed set?
Yes, sir.
Yes.
Yes, right. So is I is equal to this interval bounded? Not okay, 1 to infinity. So is it bounded?
No, sir.
The interval is 1 to infinity. It is not bounded. Correct? And therefore, is f bounded? Is f bounded?
Yes,
Is
sir.
f bounded? Yes, here f is bounded. No problem. Okay, now if I consider f from 1 to infinity to r, fx is equal to x square, right? So is f continuous?
Yes, sir.
Is so yes, f is continuous. So interval 1 to infinity is interval I closed, right? Yes,
Yes.
according to the
Yes.
so also I is not bounded. So no, and is f bounded?
No,
No,
sir.
sir.
So here f is not bounded. In the previous case, f was bounded. That means if so, which condition failed in the theorem? Which condition of the theorem failed here?
Interval is bounded.
Right, this failed. So interval is not bounded, then there is no guarantee the function is bounded or not. May not be bounded, may be bounded. So if one of the conditions failed, right? So now I define a function on 0, 1 to r, fx is equal to 1 by x. So is f continuous on I is equal to this? Yes. Is function continuous? F of x is equal to 1 by x depend on open interval 0 to 1. I am talking about open interval. Is it continuous? Yes. So my domain is 0 to 1 open. Is it continuous? Okay. Is it continuous at x is equal to 1 upon? Is it continuous at x is equal to 1 upon 100?
Yes, sir.
Yes, sir.
Yes, because 1 upon 100 is in between. Is it continuous at x is equal to 1 upon 2500?
Yes, sir.
Yes. So, so 0 is not in the interval, 1 is not in the interval. is it continuous at every x greater than 0?
Yes, sir.
Yes, sir.
Is it continuous on interval I?
Yes, sir.
Yes. Because our interval is 0 to 1, not 0 and not 1. So you choose any point in between 0 and 1, function is continuous. That's fine. Is interval bounded? Is
Yes,
interval
sir.
bounded? Yes, but is interval closed?
No, sir.
Interval is not closed. And is function bounded?
No, sir.
No, sir.
No. And therefore, why we get negative conclusion? Because one of the conditions failed. Because these three conditions should be there. If one of the conditions failed, no guarantee of boundedness. You understand? Right? Suppose I define function 1 to 2, fx is equal to 1 by 2. Fx is equal to 1 by x. Now, first question, what is answer of first question? Is f continuous? Yes, right?
Yes, sir.
Is I 1 to 2 closed? Yes.
No, sir.
So I am taking closed interval. I am including 1 and 2. I am choosing interval 1 to 2 and including 1 and 2. So it is closed,
Yes, sir.
right? So interval is bounded. Is f bounded?
Yes, sir.
Yes, f is bounded. Now, if you observe these above four examples, that means if one of the conditions failed, let me give one more example. Suppose I define a function 0, 1 to r fx is equal to x. So f is continuous. Secondly, I is equal to 0, 1 bounded, right? Third, I is equal to 0, 1 is not closed, right? It's not closed and f is bounded, but f is bounded. So what this example suggests, if these conditions are, even the condition failed, function may be bounded, but if condition failed, may not be bounded. Anything happen if one of the condition failed. You understand? So thus, what you can see, the conditions 1, 2, 3. Are these conditions necessary for boundedness? Are these three conditions
No, sir.
necessary for boundedness? No, because in this fifth example, if you see one condition failed, still function is bounded, right? Condition still function is bounded. So uh, in third example, condition failed, function is not bounded. So that means if conditions are not necessary but are sufficient, but not necessary for boundedness of f, right? Now, do you understand the meaning of this sentence?
Yes.
Conditions are sufficient. So, conditions are sufficient means these three conditions are satisfied, then certainly function is bounded. That means sufficient. These three conditions hold, function is bounded, no doubt. Not necessary means even if conditions are failed, then also it may happen that function is bounded in some cases. This is the meaning of this sentence. Is it clear?
Yes.
Right. So what is a necessary condition and what is a sufficient condition? So that is very essential to understand as far as mathematical logic is concerned. Right? And from these above examples, it is clear what is the meaning of necessary and what is the meaning of sufficient. So sufficient means what? If something is true, then this certainly this thing will happen. Right. So, but not necessary. Even if condition failed, then also it may happen that sometimes function is bounded. And in real life also we come across such kind of situations. Some conditions are very necessary, right? So if you have money, then you can purchase something. But if you don't have money, you cannot purchase. So money is necessary, right? So if you have cash, then you can purchase something. Cash is sufficient. But if you have credit card or debit card, then also you can purchase things. So now in this situation, is having cash in your pocket is necessary to purchase something?
No, sir.
No, right? To purchase something nowadays, to purchase something, having cash in your pocket is not necessary. It is sufficient. If you have cash, certainly you can purchase something, no doubt. But even you do not have a cash, then also you can purchase. Yes. So is it clear? Is it clear what I am saying?
Yes, sir.
Okay, now we want to extend our idea of this bounded function to some. See, we are going to build something, some big structure, right? We are developing our structure. Boundedness we understood, and under what condition we are sure that function is bounded. So now we want to go ahead. So let is subset of R and f is from A to R be a function. So f has, okay, so let me let A belongs to A. So what is the domain of this function? Yes. What is the domain of this function? Yes.
A.
A, right? And I am looking at a point A, which is inside the domain. F has an absolute maximum value.
Sir,
And yes,
so your screen is stuck.
just a minute. So is it visible now?
Yes, sir.
So f has an absolute maximum value at a if f of x is less than or equal to f of a for every x in a. Okay, now read this sentence carefully and is the meaning clear?
Yes, sir.
So if this is my set A and A is some point, so suppose my graph of function is like this, right? And you look at A, do you see the figure?
So there is a latency when you're writing something on the screen. We can't see it at the time you write.
Okay, there is a lag. Now, is it visible figure?
Yes, sir.
Yes.
Okay, now this is a graph of function and look at point A in the domain A. What is the value of function at A is f of A, and do you realize that in this case you choose any x in the, what is the value of function at x? Is it less than f of A?
Yes, sir.
Right, so f of x is less than or equal to f of A for every x in A. That means value of function at a point A is a maximum, topmost value. So therefore function f has absolute maximum value at A. Correct? Function f has absolute maximum. For example, if I define 0 to pi to r, f of x is equal to sin x. Right? Now, what is the graph of this function 0 to pi? Is this sin x? And at what point function has absolute maximum value?
Pi by 2.
Pi by 2.
Pi by 2. So in this case, a is equal to pi by 2. So at x is equal to pi by 2, f has an absolute maximum value. Fine. Now the meaning is clear. Function has absolute maximum value. Now second, f has an absolute minimum value at a if the reverse, opposite to absolute maximum, f of a is less than or equal to f for each x in a. That means at every x, value of function is greater than or equal to value at a. So for example, if your function is like this, if this is a graph of function, and if this is my domain A, right? And what is the point at which function has the least value? F of A. This is a graph of f. Now, is it correct that f of x is greater or equal f of A for every x in domain? Is it true in this case?
Yes, sir.
Yes, sir.
Right. Because you choose any other x in the domain, whatever x you select, value is greater than f of A. Right? You choose any x in the domain, value is greater than f of A. So at A function has least value. So absolute, throughout. Absolute means throughout the domain. Right. So for example, in particular, if I define a function for from 0 to 2 pi r, and what is fx equal to sine x. So I am looking at this function. Now can you see the graph of, so how is the graph? 0 to 2 pi, right? This is the graph of sine function in the domain. Now in this domain, if I take a is equal to pi by 2 and p is equal to 3 pi by 2, then what happens? F of x is less than or equal to f of pi by 2 for every x in 0 to 2 pi, and f of x is greater or equal to f of 3 pi by 2 for every x in 0 to 2 pi. So what is the therefore f has absolute maximum value at which point?
Pi by 2.
At a is equal to pi by 2, and f has an absolute minimum at p is equal to 3 pi by 2. Correct?
Yes, sir.
So throughout, this value is minimum, right? Now, f has relative maximum or local at a if. So relative or local if there exists some delta such that f of x is less than or equal to f of a for every x in p delta a, which is a minus delta a plus delta. Okay, now do you understand this statement? Local minimum or local maximum. Okay, suppose my function is like this. So if this is a graph of function, if I call this as a1, I call this as a2. Now look at point a2 and compare a1. So there exists a neighborhood of a2 in which, okay, let me draw some correct graph. Okay, so this is a graph of my function. So look at point a2, a1, a3. So which is the point of absolute maximum?
A1.
A1, right? Now if you look at value of function at a2, then what can you say about value of function at a2? It is not absolute maximum value, correct? But there is a neighborhood around a2, so a2 minus delta and a2 plus delta, right? So for every x in that neighborhood, what happens if we choose x here? Then what is f of x? Right? If you take x1 on right hand side, or if you take x2 on left hand side, then what is f of x2? So do you understand? f of x is less than or equal to f of a2 for every x in a2 minus delta, a2 plus delta in this small interval. Do you realize this?
Yes, sir.
Right? That means at a2, f as local. Local means in very small neighborhood, around, near that point. Local maximum. Not throughout. So, for example, Mount Everest is a absolute maximum point, right? But you look at the small mountains or hills around us; these are local maximum, right? If you look at the topmost point of your mountain around you or small hill around you, then that topmost point is a local maximum, right? Not absolute maximum is also called as a global maximum. So absolute or global, right? So absolute or global minimum, global maximum. So the difference is clear.
Yes, sir.
So f of x is less than or equal to f of a1. This is true for every x in the domain, right? F of x is less than or equal to f of a2. It is true only in some neighborhood of a2, but f of x is less than or equal to f of a1 for all x in the domain. So f has absolute or global maximum at a1. So if you understand this difference, then it's fine. So local means in the neighborhood, global means throughout. So yeah, is there any confusion about these definitions? So f has local, or relative minimum at a if there exists delta such that f of x is greater equal f of a for every x in b delta a or a minus delta a plus delta. So in small neighborhood, the value at a is minimum, not throughout. See, for example, if you look at function, this is suppose graph of a function, right? Now, this is point a1, this is a2, this is a3, this is b1, b2, b3. Okay, now you tell me about these points. Yes,
A1 and A3 are local maximums, and A2 is absolute maximum.
right. So a2 is absolute maximum, a1, a3 are relative maxima, right? So therefore, f has absolute maximum at A2, relative or local maximum at A1, A3. So f has absolute minimum or minima at
B1.
right at B1, because at B1 value is the lowest value, and relative minimum at
B2 and B3.
right at B2, B3. Right. So idea is clear. Now let us see precise example. So f from R to R, f of x is equal to x square. So question 1, does there exist A belongs to R such that f has absolute maximum at A? What is the answer? Does f of x is equal to x square is a function defined on R. Does there exist a point in domain at which function has absolute maximum value?
No, sir.
Your answer is no, right? Because there is no point at which function value is, because if you see if you choose any point, function is going above. Does there exist B such that f has absolute minimum value at B?
Yes, sir.
Yes. So this is a graph of x square, and yes, and what is B is equal to 0. At 0, function has absolute minimum value, correct?
Yes, sir.
So okay, now so the next aim is what we are interested in. So suppose I define a function on 0, 1 R, and what is my function? F of x is equal to x. Okay, is this function bounded? Is f bounded? So I have defined function on interval 0 to 1, and f of x is equal to x. Is function bounded?
Yes, sir.
Yes, sir.
Yes, because f of x is less equal 1 for all x in 0, 1. Value is not greater than 1. So of course it is bounded. Now, does there exist? So does there exist A belongs to this interval 0, 1 such that f of x is less than or equal to f of a for every x in 0, 1. Can you produce an element in the domain at which function has absolute maximum value?
No, sir.
So yes, so if you look at function is defined on this interval, 0 and 1 are not included, and of course the answer is no. There is no point in the domain at which function has absolute maximum value. Everybody agrees to this?
Yes, sir.
So same question, does there exist A belongs to 0, 1 such that f of x is greater equal f of a for every x in 0, 1? That means does there exist a point in the domain at which function has absolute minimum value?
No, sir.
No, even function is bounded. We cannot find a point in the domain at which function has absolute maximum or absolute minimum. Right. So, okay, now this is a kind of observation and we want to make a statement. Right. This is the way people develop new results. Right. Or new statements or new theorems. How theorems are created. They observe something and so now we'll make observation. So 0, 1, 2 R, right? Same function I am taking and I am repeating same questions. Does there exist A belongs to 0, 1? I am taking closed intervals such that f of x is less than or equal to f of A.
Yes, sir.
In this case, yes. And what is A in this case? 1. Correct?
Yes, sir.
I have the same function I am taking. I have just modified my domain, right? So, does there exist B belongs to 0, 1 such that f has absolute f has absolute minimum at B?
Yes.
What is answer? Yes. And what is B? 0. F of
0.
0 is right. F of 0 is less than or equal to f of x for every x in 0, 1. So now compare the uh, example 1 and example 2. So what is the difference? We have just modified domain, small modification, right? Small modification is done. Okay. Now I will take another example, f from 0, 1 to R. So I am defining f of x is equal to 1 by x. X belongs to 0 to 1. Or, okay, let me make it. X is not equal to 0 and it is 10 if x is equal to 0. So is it defined everywhere on interval 0, 1? Is this function defined everywhere on the interval 0, 1, closed interval 0, 1?
Sir, the question is not visible to us yet.
Okay, I have defined a function f on closed interval 0, 1 to R. Yeah, of x is equal to 1 by x. Right? But at 0, I am defining it is equal to 10 or some number. Is it visible now?
Yes, sir.
Okay. Now, is it defined on the interval 0, 1 clearly?
Yes, sir.
Yes.
So, at 0, there could be a problem, but at 0, I am defining value of function to be 10. And then my question is, does there exist A belongs to 0, 1 such that f of x is less equal f of A for every x in 0, 1? Yes,
No, sir.
no. Why no? Because if you look at the graph of this function, at 0 function is 10, no problem, but you fix there is no point at which value is a maximum. That means if you go closer and closer to 0, function becomes larger and larger. So what is the problem? What is the problem? Even I am taking close interval, still there is no point at which function has absolute maximum value. So what could be a problem? What do you think?
Discontinuity.
Discontinuity. So is f continuous on 0, 1?
No, sir.
No, not continuous at 0. Basically, it is not continuous at 0 because at 0 limit does not exist. Right hand limit is infinity. Even function is defined at 0, but limit does not exist. It is not continuous at 0. So continuity fails. And therefore, now we can make up what will be the statement. So this is again a difficult theorem too, because boundedness theorem is first theorem we discussed yesterday. Maximum minimum theorem, or sometimes it also called as a max-min theorem. So what this theorem says, so let be a closed and bounded interval, right? So if f from I to R is continuous, then okay, so these are the conditions. Are these conditions same as the conditions which are there in boundedness theorem?
Yes, sir.
Same conditions. The conclusion is we are going to, because we are here thinking about maximum minimum. Then f attains absolute maximum and minimum on I. That is, what does it mean? F attains. Attains means that is there exists alpha, beta belongs to I such that f of x is less than or equal to f of alpha for every x in I, and f of x is greater or equal f of beta for every x in I. That means there is a point at which function has maximum value, absolute maximum value. There is a point at which function has minimum value. The statement is clear. Yes,
Yes, sir.
right. So alternatively, so let f of I. I am looking at f of I means what? The collection of all images of function. If we apply function on every point of interval I, then look at the images. Right? Is it a set? Do you understand what kind of set is it? Just images.
Yes, sir.
Then so maximum means what? So if this is a set, then maximum exists means what? Then there exists alpha, beta in I such that if alpha and beta are in I such that f of alpha is equal to maximum of f of x belongs to I. But f of alpha and f of alpha, is f of alpha member of this state f of I? Is f alpha member of fi?
Yes, sir.
Yes, because alpha is a member of interval, so corresponding element f alpha is member. And it is a maximum means what? If, see, recall this, if alpha is a member of and alpha is maximum of state A, then can I say that alpha is supremum of A? If maximum element exists, then it is a supremum, correct?
Yes, sir.
Yes, sir.
That means f of alpha is a supremum of this state, image state. And what is f of beta is minimum of all fx. But minimum element exists, that means it is infimum of state fi. Fi is a state. So this is an alternative way to look at this statement. But what is the hypothesis? What are the conditions under which this holds? Are the same conditions. Domain is closed and bounded interval and function is continuous. Same conditions, the conclusion is different because we are looking at different aspect of the function. In the previous theorem, we were looking at boundedness aspect. Now here we are looking at the maxima, absolute maxima minima aspect. But of course, to prove this, we need the previous boundedness theorem. Right, statement is clear.
Yes,
Yes,
sir.
sir.
So my domain is I, A to B, and my function is continuous, right? Then my function is continuous. Then there is a alpha in, so f of alpha is maximum. There is beta in the domain at which value is minimum. So f of beta. Right. So this is the situation actually. But then question arises, can you have, is it possible that there is unique alpha under these assumptions? Or you may have more than one values of maximum or more than 1 points of minimum. Yes, alpha 1 and alpha 2. It may happen that the value of function at alpha 1 and alpha 2 is maximum. Same. It may happen. The function is continuous, domain is closed and bounded, so it may happen. But there is at least 1 point, at least. We are not saying that exactly 1 point at which maximum is attained, and there is a point at which at least 1 point is there at which minimum is attained. So do you understand what I want to say? Right? Is it clear?
Yes, sir.
Yes.
So what is given? So I is equal to AB is a closed and bounded interval. So our assumption is domain is interval, closed, bounded. F from I to R is continuous. Function is continuous. Then what is our claim? What is our claim? There exists alpha, beta in I such that f of alpha is maximum or f of alpha is equal to supremum of f of x, x belongs to I, right? And f of beta is minimum or f of beta is equal to infimum of all values, all fx. This is our claim. Correct? Yes. So, okay, next time we'll see the proof. Before that, so let P is equal to set Fi. And what is set Fi? All values or x in I. That means just collect the values. This is set P. So, for example, if f of x is equal to 2x and my interval is 0 to 1, then what is set in this case? F of I. Can you tell me what is f of I in this case? All those values for which x is in 0, 1. Right? What is set I, f of I in this case? 0 to 1 and f of x is equal to 2x. So what is the value of function at 1? Is 2, right? And since its graph is straight line, so what are all the images? Is this set same as 0 to 2?
Yes, sir.
Right. Because we'll see later on, it is also interval, but anyway, here you can understand what is the set of all images. That means you choose any x, what is f of x, choose another x in the domain, what is f of x, collect all images, that is set. That, okay, so next time we'll discuss the proof. There is a point at which maximum, absolute maximum exists, right? So next time we'll continue this. We'll stop here. So any doubt?
No, sir.
Okay, so we'll stop here.